Hello, Physics 123 students. I'm working toward getting your tests ready and start grading those. But what I'd like you to do first is to kind of run through this video and kind of self-grade yourself. And that'll give you an idea of what you think you did on the test. Plus, more importantly, it'll give you a chance to correct your mistakes far better than like you could with a few little notes here. So let me dive right in here so the video doesn't go too long here. It is only a half exam. It's got these 2.5 questions. Let's start here with this first one. It's got a part A and B, and it looks like it's got a little pendulum and a bike rider. And of course it says on a hot day, so 40 degrees, a pendulum is built with a small compact speaker, a 1.25 kilogram speaker at the end of and I'm going to call that a 1.75 meter string. So 1.75 meter string. So hopefully you converted your units here. And the first part just says, if this simple pendulum is set into motion by hitting the stationary speaker to the left with enough force that it moves to a maximum of 61.2 centimeters, and depending on how you want to do this, you may or may not convert to meters, but I will. To the left, okay, so the negative direction before returning, and continues to swing back and forth, write an equation of motion. So you can see this is right from chapter 15. I'll just put here number 1, I'll put A, and we learned that the position back and forth as a function of time is going to have some amplitude, some cosine, omega t, and then some kind of phase shift, meaning it's not really a cosine, it could be a sine, it could be a minus cosine, it could be a minus sine. And so let's talk about that. Probably the easiest one to do is right here at the beginning, because they directly tell you how far it moves to the left. And so they're saying here to the left with enough force that it goes a maximum distance. And so that's what the amplitude actually is. So it might have been a little easier if they had said this is the this is the amplitude, but instead they say this is the maximum. Anyways, that's very clearly then the amplitude. Now, the other thing to catch here is it goes left first. So if you're making a plot and using the traditional, left is negative, it would look like this. And so there would be a phase shift of the cosine function. So you could continue to write it as a cosine function with a phase shift of, and I got to think about this. Let's see, a regular cosine function looks like this. And if you then shift it to look like this, you're shifting the function left by pi over 2. So a plus pi over 2 would be the phase shift. So you can write this as either a cosine omega t plus pi over 2. I think it would be better just to write it as a minus sine omega t. That might be the better option. So there it is. We have the amplitude. We now have the phase shift, however, which way we want to write it. And we have the angular frequency. Although, sorry, we don't have it yet. We could get it because the angular frequency, then we can just go back to what was worked out in class, or you could rederive it. But this was intending on you just kind of look this up. I got to remember myself, square root of G over L. All right, and then to get a number here, G, as you know, is 9.8, and the length, this is where we want to watch our units, because this is in meters, so we've got to have our length in meters. So this is 1.75, and then the square root, and it looks like a 2.37. All right, so if we put all that together, we get this equation. Position as a function of x equals a 0.612 meters, or 61.2 centimeters is fine, negative sine, and then the omega is the 2.37t. Or, like I said, you could put cosine with a plus pi over 2. So there's the first half of the problem. Just writing out the equation. And then to kind of blend a couple chapters together, this speaker then has a biker riding towards it, and then they're going to get a Doppler effect. And as it swings back and forth, you're going to get movement of the source of the sound and a movement of the observer. So if the speaker produces sound waves at a frequency of 850 hertz, what is the highest and lowest frequency heard by the observer on this bike moving towards the pendulum speaker system? So as the picture shows, the bike rider is going this way. And of course, the reason there's a high and a low is because sometimes the speaker is moving towards the rider, so that would be an increase in frequency, and then sometimes away, and so that's a decrease. Now the biker's always moving towards the pendulum, so that's an increase. And in fact, that increase will always be more than the either increase or decrease. So both answers are going to be higher than 850, but there will be a higher and a lower one. And so we need a couple of speeds here. You might remember that the Doppler effect here, this is kind of the crutch of the problem, would involve the speed of the wave and then plus or minus the speed of the observer, and then speed of the wave minus or plus the source multiplied by the original frequency. So we've got three different velocities to think about, their directions, and of course the main frequency, what I'll call the real frequency, the actual oscillations, is that 850. So let's look at the velocity of the sound. General rule is keep the room temperature one in mind, 345, unless they give you some kind of temperature to work with. And this one told us it was a hot day, 40 degrees. So 1 plus 40 divided by 273, square root of that, times 331 is 354.4 meters per second. So that would be the speed of our sound waves. The speed of the observer is probably the easiest of the three because they directly tell us the bike is riding at 6.25. The speed of the source involves a little more thought. Might as well treat it like a pendulum swinging, and so we know the maximum speed is omega A for any oscillations. We could also, I guess, go back to Physics 121 and just do kind of a principle of conservation of energy to find the speed. But given the material for this section, let's do it this way. And plus, we have these numbers from above. This is the 2.37 for the angular frequency, and the amplitude is 0.612. And so this will give us the maximum speed of the pendulum. And it looks like it's a 1.45 meters per second. And like I was trying to mention in this picture, depending on where in the cycle, the maximum would always occur when it's down here at equilibrium and going towards the bike or away from the bike. So I guess our two calculations would look something like this. The top would always be 354.4, and the observer would always be 625, and would always be going towards the source. So that's going to be just a plus sign. What changes direction is the source of the sound. So this will be a 354.4, and it would be a minus when it's going towards the bike rider. And so that's going to give us the higher frequency. It's going to be a plus sign when it's going away from the bike rider. But the speed is only a 1.45, and then of course times 850. So let me do the high one first, and then the low one. All right, so why don't I, the only thing changes is down here in the bottom, so maybe I'll kind of incorporate the two together. Across the top, I'd get 354.4 plus 6 1/4, and I'd be multiplying that by 850. So there's the top. Let me divide that by, and I'll do the high one first. So 354.4 minus 145. And so 868.5 would be the higher frequency, and this is in hertz. And then the lower one, let me just copy that numerator down there, and then also divide by the 354.4, and then this time let me add the 145. And it looks like it is an 861.5 hertz. Okay. And so there's the second half of problem number 1. All right, good. Hope that went well for you. That was our first of our harder ones. Let's move on to problem number 2, and it looks like it has 3 parts, part A, B, and C. Looks like, again, it's got some oscillations tied in with some waves. We've got a mass, which I'm going to instantly change into kilograms. So 0.255 kilograms is attached to a vertical spring with the other end of the spring attached to the ceiling. Spring constant's 125, and the units are good, newtons per meter. What is the oscillation frequency of this mass spring system? Well, this is more of a plug and chug, so both of these first ones are plug and chug, and rightfully so. That's kind of how I thought I would start it, and then kind of blending things to make it a little bit harder. But we know that the period is the 2 pi times the square root of m over k, or we know that omega is k over m. But the big thing is the period is 2 pi over omega, or the period is the reciprocal of frequency, whichever method you want to get to. The frequency then being the reciprocal of the period would look something like this. All right, so then I just need to plug stuff in here. So the spring constant is 125. The mass is where you got to do a little bit of converting of the units and go 0.255. I'll take the square roots, that's the omega, divide that by pi, also divide it by 2, and I get about 3.5. So it looks like by itself it would be oscillating at 3.52 hertz. And again, right out of chapter 15, more oscillations. And in fact, B's a little harder, but again, straight out of what we did in chapter 15. Here it says, now we want to change this frequency. So we've got an engineering problem. We've got some oscillations. We want to increase it to a frequency of 6. We're going to add a second spring. And so I guess it would look something like this. The same real equation. It's just now, you might say, we have an effective K. And the effective K is the two acting together. And of course, we talk about this, and sometimes you can hook a spring in parallel and sometimes in series, and there was a little different formula to get the equivalent one. Let's talk about that when we get that far, but I'll just put in the 6, and then the 2 pi, and the square root of the equivalent over the mass, and let's do a little bit of calculator work to get the equivalent. So if I bring the 2 pi to the other side, so I got 6 times 2 pi, that's what you get when you move that over to there. If we square it to get rid of the square root, then we bring the mass, we get an equivalent spring constant of 362. So that is the equivalent we want of the two together. And since we're hooking them in parallel, the equivalent is simply the sum of the two. So to get the spring constant of the second one, we're just going to subtract off the original one. So, like I said, the two acting together need to be equivalent of a spring of 362. So if we were to put a second spring that has a spring constant of 237 newtons per meter, the two together would give us just the right frequency, which is the 6. So that's how we're going to kind of increase the frequency. All right, so then the last part of that then makes us jump over into, I guess, the wave stuff of chapter 16. And so we're going to let this oscillating mass initiate the waves. And it says, after the second spring is attached in part B, so the frequency would be a 6 hertz. The engineer takes and they give us the mass and they give us the string and then they hang it over the side like the picture shows and says like we did in the lab, and that gives us a little tension. And so let me just point out then the tension would be mg. And I suppose we want to be careful here because now we got 3 different m's. We've got the m of the weight going up and down, that's 255. 0.255 kilograms. We've got the weight of this string, which would be 0.0255. So not the same numbers or the same set of numbers, so be careful with that one. So that's the mass of the string. And then we've got the 0.075 for the mass hanging over the side of the pulley, which is what gives us the tension. So careful not to mix those, but this is where we get the tension here. And so we'll go 0.075 times 9.8 to get the tension. So 0.075 times 9.8, and it looks like we've got a 0.735 newtons for the tension. Now, what's called the mass density is referring to the mass per length of the string. And so I'll use an m, and let's be careful, it's not the same m, this is for the string. And so as I mentioned a moment ago, and we'll continue, this is the mass I want for this case. The length is 10 meters. And so we're looking at 0.00255 kilograms per meter for the mass per unit length. And of course I'm interested in that because coming right out of chapter 16 says the speed is based upon those two factors, what I call the elastic factor and the inertia factor. And so the thing that makes it snapping back, the tension, is the 0.735 newtons. And the thing that's resisting the change is the inertia. And the combination of those two gives me my speed. So I already got the 0.735 in the calculator. Let me divide it by 0.00255, and then let me take the square root of that. And so it rounds to a 17.0. So 17.0 meters per second. And again, notice this is my clue here that I want this in kilograms to cancel off with the kilogram that's in the newtons for the tension. Okay, so there is the speed, because ultimately this question asks for the wavelength, And so the last step here is to take the velocity and divide it by the frequency, and the hertz and per second are the same and cancel off. So I get that speed and divide by 6, and we're looking at about 2.83 meters. So that's the wavelength. Cool. In fact, I got this from a harder problem. Probably shouldn't even mention it, but the harder problem said estimate how much string is hanging over the side, because when you look at the picture, you got 3 half wavelengths. So if I divide that by 2, that's a half wavelength times 3. And so this part of the string must be 4.2 meters, and the whole string was 10 meters anyways, and you get 5. So apparently 5's hanging off the side. But that is not part of our problem. So I made it a little easier than that. Actually, maybe quite a bit easier than that. All right, so there's the second hard one. And now off to the last one, which is the half problem. It's only worth 10 points and hopefully looked a lot easier. And part of that easy is it didn't blend chapters together. It was just right out of 17 with sound waves and sound level. It does have 2 parts to it, but the first part, maybe I should show you the problem in case you forgot. It says a loudspeaker, and it gives you the frequency and tells it goes outward equally in all directions. And so this is hopefully one of these ones that look like on the practice exam, that it spreads out equally in all directions. And so this is the power. And so if you were going to go and calculate the intensity, and the reason I guess I'm going to do that is as I read the question, it says, what is the sound level? Well, sound level is based upon intensity. And of course, intensity and amplitude are related. So I'm going to need this intensity for both part A and B. So I've got my 1 watt for the power, and the area sets it spreads out equally in all directions. And if I were to draw a picture of a speaker with the sound going out, it would, spread out on a sphere, and the surface area of the sphere is 4 pi r squared. So at 25 meters away over here, it's still going to be really loud. This is 1 watt. It's a lot of energy. Remember, the threshold of pain was 1 watt per square meter. So if all this was 1 meter, there'd be 120 decibels. And so that's what you would probably get when you're close to it, 120 decibels. But we're quite a bit away, so it's not going to be at the threshold of pain. It's still going to be reasonably loud. And of course, you can get that. Let me get the surface area, 4 times pi times 25 squared. So there's the surface area. So if I go 1 divided by that surface area, I'm looking at an intensity of about a 1.27 times 10 to the minus 4 watts per square meter. So there's the intensity. And so what we called the sound level was to take your intensity and compare it to a reference, take the log of that and multiply by 10. So I will take that intensity, and the reference is what we called the threshold of hearing, 1 times 10 to the minus 12. And so this is the ratio between the lowest your ear can hear and how loud this is. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Wow. So in the hundreds of million times greater than what your ear can hear. No, well, you can see times 10 to the 8. There it is. Because 10 to the minus 12, 10 to the 8th. So anyways, this is 100 million times stronger than just the minimum you can hear. And it's amazing that, this really isn't that, it's loud, but not damaging and not overwhelming. So you're amazing that your ears could hear such a low intensity and then also this loud intensity without damage. Anyways, but to take the log of that and multiply by 10 would get us our sound level. and that's 81.0 decibels. So there is A. And the last part of this was that the intensity of our sound waves was made up of 4 factors, and one of those is the amplitude. So we know the intensity, and we know these other things. This is the density of air, this is the speed of sound, and then this is the angular frequency. And so with a little bit of calculator work, we should get the amplitude. So let me come back and get the intensity. I don't know if I should go up and just copy it. Maybe I'll do that or retype it. But there's the intensity. And if I bring the 2 over, I can multiply by 2. I can then divide by the density, 1.2. I can divide by the speed. And remember, the general rule is they don't tell you the temperature. They're kind of implying room temperature, which the speed works out to be 345. So unlike number 1, where they said it was a hot day and we had to use then the higher temperature, they don't say anything, so I'm going to use the standard 22 degrees and use the speed of 345. Then I will divide it by the angular speed, angular frequency, and it's squared. So maybe I should remind you and myself that the angular frequency is 2 pi times the frequency. So when I square that, I have a 4 here. I square that, I'll just do pi squared. And then I'll do the frequency, 256 squared. And then all of that then should be this s squared. So final step, by taking this square root, gives me a distance of 4 points, looks like about an 88 times 10 to the minus 7 meters would be the amplitude. All right. Well, hope that went well for you, and I look forward to grading your exams. Take care.